First of all, is if I keep it at this distance, does that work for everyone? Nice. Okay, welcome all to my talk from fieldwork to foundation models, satellite monitoring, ecological monitoring, Jesus, with Sattelite AI. As said, I'm Jordi de Lange. I work at Spheer.ai I've been doing that for 1.5 years. And before I start, I will tell you very quickly about what we'll be talking about today. So first of all, I'll be telling you about the quick background on the problem that we identified and our proposed solution to that. And without any real surprise, this has to do something with AI, for which, of course, we need data, which I will also tell you about, followed by the rather straightforward approach that we had used in previous years, and afterwards the smarter approach, which we're currently working on, as well as a short view into the future of what I would think ecological monitoring would look like in the coming years. So this problem, right? We grow increasingly conscious of our natural environment. It is a limited resource which is being used all over the planet, and I hope we can all agree that it warrants some protection, which is hard because in order to do that properly, we need good data, right? In order to deal with our nitrogen problem, which we currently have in the Netherlands, we need to know where this is being deposited, where it is being spread from. And data like this is currently being gathered. Ecologists head out into the field every year. And while that's nice, it's not ideal. It's quite an involved and expensive process. And most nature reserve areas in the Netherlands are mapped out quite well, but if we're lucky, every 6 years, and if we're a bit less lucky, every 12 years, which makes it very hard to identify trends, right? If I, as a local government, take a measure in order to protect something, and I need to wait 6 years until the next measurement to see if something actually changed, that's not really workable. And we think it can be done way better. These are the kind of maps that are being made by the ecologists. So they head out into the field, they draw all these shapes in to make it a bit more manageable. And for each of these shapes, various things are recorded. The type of plants growing there, stuff like that. But again, quite infrequently. So the solution to this, in our minds, is to supplement this existing monitoring, which is already being done, right? And we can use this in order to train AI models, in order to actually give predictions on a higher temporal scale, on a more precise temporal scale, and a more precise spatial scale. Because we can do this type of prediction every year instead of every 6 years. And because we're not bound to these shapes that the ecologists draw in, we can actually provide a much more detailed prediction. And in order to be able to do this, we need data, of course. More specifically, we need labels and imagery. The label data can be taken care of because these maps are already being made. This needs to be extracted, of course, and because we're dealing with rather messy human-made data here, this is still quite a lot of work, but it can definitely be done. And then we need to combine these labels with some sort of imagery. And there's a couple of sources for this imagery we could use. First of all, we could buy or rent a drone and drive out to the fields, make a couple of nice pictures. Upside, these would be incredibly high resolution, which is really nice. Downside, we'd rather have this for the entirety of the Netherlands, or even more, and that would be a lot of work. What already is available for the entirety of the Netherlands, luckily, is airplane pictures. So once a year, the entirety of the Netherlands is covered by aerial photographs, which is way nicer because there's a lot more area in there. But there are still some problems with this, namely that it's only a one-time snapshot, and vegetation and nature is changing all throughout the year. And this is really important information which we would like to include somehow, right? If we look at leafy trees, they are green in the winter and brown in the green in the summer and brown in the winter, whereas coniferous trees are green all year round. And we'd like to capture this somehow, which is where the last option, satellite imagery, comes in, which is the obvious one. We choose this one because it both covers the entire globe, so we have a lot of data, and it does so about once a week. so we can create almost a video of the entire Earth's surface. This imagery is different from the imagery we usually work with, or that imagery that you and I capture with our eyes, in several ways. Most of us can see in 3 colors, roughly blue, roughly green, and roughly red. The satellite actually expands this massively. So instead of going from about 400 to about 700 nanometers, it can sense 10 colors, going from about 400 to just slightly over 2000 nanometers, which means there's actually a lot more information being captured than you or I could simply just see by looking at it. Here's an example of this. So this image has its red channel replaced by an infrared channel. This causes a lot of the trees and vegetation in this image to be very red, because they actually reflect infrared quite well. And if they were to dry out a bit, they would reflect infrared differently, which means that this information, which is being captured by the satellite, these 10 colors, are actually really powerful and really useful to us. The second big part about satellite imagery is that it's periodic. So because the satellite comes over every piece of ground roughly once a week, we actually create a sort of video file, which we can then use to then actually make use of this temporal structure in the data. Sadly, the resolution of this image is quite low, so we're dealing with about 10 by 10 meters per pixel, which would cover this room in 4 pixels. So there's not a lot of actual acute detail there, which means that we are actually only dealing with single pixels at a time, or at least we choose to. So the way we deal with this data, right? We have these satellite photos. I stacked them here, and you could imagine that if you were to scroll through this stack, you would basically see the video that I just showed you, right? So as we go further into the slide, into the depth, we advance in time. We stack these per pixel. Again, because the resolution is quite low, there's not a lot of detail visible anyway, and because we have these about 50 measurements for each year, each measurement consisting of these 10 colors, there's actually a lot of information already if we just treat these per pixel. So we have these single pixel time series. Some of the data will not be usable due to clouds or measurement errors, so we remove those, and we end up with these cleaned pixel time series. Each unit consists of these 10 colors the satellite is able to measure. We then need labels, which in real life is an involved and messy process, but here I can just say that we simply sample for each pixel on the in the satellite photo, we simply sample the label map and we get pixel labels, and I will spare you the process of dealing with ecologist created data, which I really like them. I like that they're doing it, but the data isn't always the cleanest. We take these labels, right, and then we can just combine them with our pixel time series to create rather straightforward data to label pairs. And with this, we can just do some machine learning, right? We can train a model on this and then predict for years in which these ecologists didn't make a map of a natural area. In order to do this, we use a transformer encoder. For several reasons, but mostly because it works really well with this temporal component that our data has, right? They're the time series of a single pixel. Really quick refresher of a transformer encoder. Say that this is an example from BERT, which is a model by Google. Say that we want to classify this sentence, right? Which has to do with medicine. The way you could do this with a transformer encoder is to basically chop this sentence up into little bits we can call tokens. These will then enter the model, where the attention mechanism will be responsible for basically combining the meaning of each of these individual bits of information. And at the end, a class label will come out, and if this is trained well, the class label will of course correctly identify the sentence as being about medicine. We do something quite similar. So we take one of our satellite pixel time series, right, consisting of all these separate measurements made by the satellite each time it passes over, and we feed each of these measurements as the single units of information into the network. The network will then process this and see that, for example, oh, well, it's green in the summer, but it's brown in the winter, so it's probably a leafy tree. At the end, through where's my light? There it is. Through a pooling layer and linear classifier, we end up with a prediction, which we can compare to our labels to calculate a loss, and then through some backpropagation, we can improve this system until it works really quite well. What do we end up with then? Well, this is a photograph of a field of heather, and we predicted heather using this picture. You can see that it works quite well. The darker bits, like here for example, that's really heavy heather, and it manages to separate that out quite nicely. And this image looks quite spatially consistent, right? There's a lot of big continuous areas of heather, but again, we're dealing with only the single pixels here, so this is all just emergent from the good training. And because we do this every year, we can create nice overview images like this, where in this central plot of land, a certain type of grass called zeekweek or sea couch in English has been spotted, and it's not really wanted there. And through grazing with horses and sheep, or cows and sheep, I believe, they try to eradicate this type of grass, and we can see that it really works quite well. Whereas otherwise, the municipality would have had to wait until the next mapping round comes along for this type of for this area here. And now we have a very nice and detailed view, basically immediately. So this method really works quite well, but it also has some flaws, right? Creating maps like this still requires significant manual effort. If this could be done easier, that'd be nice. At the end of all this effort, we have mapped for only one type of vegetation, right? So we train it on specifically heather or specifically sea couch. It requires already existing labels. So if you want to keep track of something new, that would be very tricky, because if it hasn't been mapped out yet, how do we train a model on it? So even though it works quite well, it's not very scalable. We ideally do this in a smarter way, right? Because in an ideal world, you would do something like this through few-shot learning, right? You would give a couple of examples. Well, this type of vegetation is what I'm interested in, and this type of vegetation is what I'm not interested in. And you'd ask a model, which ideally has some sort of inherent understanding of nature, to simply find the types of nature which you are interested in. You would then want to do this with an easy way to provide these labels, right? To say what you are interested in. You would want a convenient way to view the predictions, and of course, this should all be directly accessible to and usable by the end user. These are all very interesting problems, but since only the top one is an Pygrunn problem, allow me to just focus on that one for now. A model which understands nature. So how can we do this? Well, we can actually take quite a lot of inspiration from LLMs like GPT. These have been trained on massive amounts of data, which again we have, right? Because our satellite, well, okay, the satellite we use has been orbiting the Earth for 7 years now, making a picture of the entire Earth surface every week. These models, these LLMs, have then been trained on this massive amount of data. So in LLM's case, basically the entire internet, in a self-supervised manner. So GPT has been trained through next token prediction, which basically means that they give it part of a sentence and ask it to predict what word comes next. And you can imagine if you do this over and over again, the model slowly starts to come to an understanding of language, of grammar, of meaning of words, and eventually even the recollection of facts and such. And this works, right? We've all used GPT, I assume, and we can attest to the fact that this works really well. And we actually are doing something very similar with our satellite data. One possible way you could do this is through a masked autoencoder. So how does this work? Well, we take our ground truth, right? Just a single pixel time series, and we mask out part of it. In this case, I mask the second, third, and fifth measurements that the satellite made. So each of these measurements, again, are these 10 colors that the satellite is able to see. We pass this masked truth through an encoder model, so just can be any type of neural network, which creates an embedding, which is going to be important later, so remember that. This then goes through a decoder, which tries to reconstruct, to the best of its abilities, the original ground truth. At the beginning, of course, it will be very bad at this, because it has only very little information. But by comparing this predicted truth to this ground truth, we can actually come to a loss and train this entire system until it really works quite well. And at the point that it does work well, we immediately throw away most of it. Because what we are interested in this is this just the ability of this encoder model to turn this ground truth, or this masked ground truth, but also this original ground truth, into an embedding, which somehow contains all the information necessary for this decoder model to reconstruct this ground truth. And at this point, this encoder model becomes what I'd like to call a foundation model, right? It has gained an inherent understanding. It is able to effectively interpret this rather messy, noisy, even masked out satellite data into a nice, neat embedding vector, which is then usable for multiple things. So you could reconstruct the original one, but you could also do other things with it. And if we can do this for one pixel, we can do it for a lot of pixels. And if we can do it for a lot of pixels, we can do it for entire maps, which gives us an embedding map. So what do I mean with this? Well, if we look at this, right, the color here is indicative of the embedding of the pixel underneath it, meaning that similar colors are probably meaning that the type of nature underneath is very similar, because it has been interpreted by this foundation model. And if we look at this bit of green and this bit of green, we expect the type of vegetation underneath it to be similar, and we can see that it is indeed the case, because it's this forest and this forest. The same if we look at this area, which, if you can trust me, which I think you can, is filled with a lot of heather, as is this area, so we would expect similar colors in both. And we do. We see a sort of pinkish purplish color here and a purplish color here. So this raw photograph has been interpreted very nicely by our foundation model. What we can then do is say that we take this picture, right? And I, as an ecologist, hypothetically, am interested in these woodland areas. And I'm not as interested in these more open field areas. If I take the embeddings that belong to these areas and I collect them into a positive embedding sample and a negative embedding collection, we've actually turned this rather weird problem into a quite straightforward one, right? Because if we have positive and negative embeddings, we have positive and negative samples, which means we can just train a classifier on this and create a map without the need for this label data. And the clever bit here is that because these embeddings already have been interpreted by our foundation model, this network actually doesn't need to be a very big neural network. In fact, it doesn't need to be a neural network at all. We can simply do this with a very straightforward regression model, or a support vector machine, or a random forest, or whatever classification method you would like to use, because they've been interpreted and made nice and clean already, these embeddings. So we actually did this. This is a thing that exists and is currently in alpha. We call it Carto. And I'll give you a quick sort of show how it works to really drive the point home that this is actually really cool. Say that we're an ecologist, right? And we're interested in forests, which I know isn't super exciting because we can all clearly see it, but that's why it makes such a good example. If I were to make a map for something which we can't see, you just have to trust me, way less interesting. So we give a couple of examples which we can use, which we are interested in, and a couple of examples of bits of land which we're not as interested in. And because this map underneath it already has these embeddings calculated, right? We can actually very, very quickly train a model on just our positive and negative samples without the need for this long training method based on the labels which we had to do before. So we can create a map like this in about 30 seconds to a minute, which is really nice. Like, it captures the forest really quite well. But what if I, for example, decide that these bits or this bit of sort of a bit loose treed, like sparsely treed area, I don't consider that forest actually. I'm not that interested in that. I can just give a couple of more negative examples, retrain the model, and it'll exclude those. Here we can see the difference again. So now it's a lot more critical about how dense the forest needs to be before it can be considered a forest. And this flexibility is really nice, right? Yes. And in my honest and of course completely unbiased opinion, systems like this are the future of ecological monitoring. Because already it is possible to create maps of quite abstract concepts, right? It's very flexible. It can deal with abstract concepts. Also way more than just forests. We've quite successfully tried this on the sea couch that I mentioned before, as well as heather and I think, well, yeah, a lot more stuff, obviously. Its interactive nature lends it really quite well to rapid iteration, as I demoed, which means that we can actually achieve better maps with this possibly than with our old method, because we can focus on areas which are apparently very hard for the model to classify. And the fact that we don't need the pre-existing label data, because our foundation model is a very capable interpreter of the satellite imagery, means that more use cases can be found, right? If I want to track something new, I don't need to wait a couple of years for the ecologists all throughout the Netherlands to make maps of the type of nature which I am interested in. And it's relatively intuitive use, means that little user training is needed, so that these ecologists themselves can immediately directly use it and do something which they deem valuable. If we zoom out a little bit more, in the very near future, we're working on multi-class predictions and maps. This is quite straightforward to add, right? Because we have these embeddings which have been nicely interpreted, and we can just do multi-class prediction on this instead of our binary ones, which I just showed you. There's no reason why this couldn't be expanded to urban and other non-ecological use cases. This whole process of pre-training a foundation model which understands the data is really quite flexible, which is also why it works so well for language. We are currently working with only the single pixel time series, which works quite well. But of course, the spatial information can also be important. And incorporating this somehow is something we're currently working on. And of course, foundation models have very broad applications in monitoring. It can be used for a lot of different things. And if you have any more good ideas, you can tell me, and then I can tell them, and they'll be very, my colleagues there, they'll be very impressed with me. Yeah, so that's kind of it. I want to thank you for listening, and I'd like to ask you if you have any questions.